Here's a rigid body kinematics question which looks at this sort of link mechanism, and it's asking us to find an expression for the angular velocity of this bar in terms of x and a. So x is essentially the distance from this fixed point C to point A, and lowercase a is the acceleration of the other end of the mechanism. And this is the kind of question that you might get if you're doing some form of engineering, probably in your first or second year. And if you would like to see anything similar to this on the channel, let me know in the comments. So the way to do this, especially because we don't actually have any numbers in here, is to first of all use the fact that the velocity of point C is equal to 0. So that's going to be our starting point, essentially. And then we're going to use that to move to another point on the rigid object, which is B. So first of all, we put the coordinate system at C, and we use this to find an expression for the velocity at B. Once we do that, and once we know the velocity of B, or once we know an expression for the velocity of B, we're going to take our coordinate system, we're going to place it at B instead, and we're going to move to find the velocity at A, right? So A is a point on the same rigid object as B. So they're both part of this bar, which is rigid, which means you can apply Euler's equations for a rigid object. Note, you cannot jump from C to A straight away because point C and point A are not on the same rigid object. So VA equals VC plus omega cross CA. This is not correct. So I'm just going to cross it out, and it's not correct because A and C are on two different rigid objects. So you can't just apply that equation like that. So essentially you have to apply Euler's formulas twice, and then we're going to put some constraints as well, and that's going to help us find what omega is. So remember, omega is the angular velocity of bar AB. We don't know anything about the angular velocity of BC. We only know the acceleration, and we only know this distance, which at this point is x, and initially it started from 0. So let's move on and apply. Let me just remove a couple of things from here. Let's place the coordinate system at C. So we have our x, our y, and let's try to find the velocity of point B. So we have the velocity of point B equals, and then we have the velocity of C plus the angular velocity of bar BC. So let's call that omega BC cross the position of B, which is CB. Right, so that's the position vector of point B. Now, we know the length of the bar, which is lowercase b, but we don't really know the components because we don't know the angle, but we can sort that out. So if this angle here is theta, right, then I can draw a vertical line like this, and I'm going to end up with a right angle triangle. So we have this kind of situation here where this is theta, this length is b, this is x over 2, so we can find some sines and some cosines and so on. So we know that cosine of theta is the adjacent over the hypotenuse, so that's x over 2 divided by b, which is x over 2b. And we can also find sine of theta. So sine of theta is the square root of 1 minus cosine squared of theta. So that is square root of 1 minus x squared over 4b squared. So sine of theta is the square root of 4b squared minus x squared divided by 2b. So Knowing the sine and the cosine will let us find the components of CB. So we have C here, this is B. So we can now put some values in here. So we've got the velocity of B is equal to the velocity of C, which is 0, and then plus, we have the determinant I, J, K. I'm putting quite a bit of space because we're gonna need it. So omega BC is only gonna have a K component. So we have omega BC here, which could be positive or negative. We don't really care at this point. And then CB has two components. So the horizontal component is x over 2. So that's x over 2. And then the component, the j component, is this distance right here, which is b sine theta, right? So sine theta is this. So b sine theta is going to be square root of 4b squared minus x squared divided by 2. And then we have 0 over here, right? So we can find the x and y components of VB. So we have I multiplied by minus omega BC times the square root of 4b squared minus x squared over 2. And then minus j. And then we do the same thing. So this is going to be 0 and then minus. So we have minus omega BC times x over 2. So this becomes minus omega BC square root of 4b squared minus x squared over 2 times I, and then plus omega BC x over 2 times j. So that's the velocity of point B. Now, we don't really consider this to be a known value because we don't know what this is, essentially. But we'll leave it as such, and we're gonna use it to further to continue the solution and find an expression for the velocity of A. So we have that at A, the velocity of A is going to be equal to the velocity of B plus omega AB. So this is the angular velocity that we have to find, and then cross product with BA. So that's essentially it. Now, to be able to do that, what we did implicitly was we moved this coordinate system from C to B. So this is Y and this is X. And everything now we measure with respect to point B. So B is our new origin for the coordinate system. So let's write it like this. We have the velocity of A is equal to the velocity of B. So the velocity of B is minus omega BC. So I'm just going to copy paste that expression. So 4b squared minus should be x squared over 2 times I, and then minus or plus, in this case, omega BC x over 2 times j. Right, so this is just VB. Now on top of that, we have to add this other determinant. So that's going to be I, j, and k. Omega AB only has a z component. So that's omega AB. And BA is basically this, right? Now, this angle is the same as the angle theta here because this is an isosceles triangle, which means that the x coordinate of A with respect to B is going to be x over 2. So this is x over 2. And the y coordinate is going to be the same y coordinate that we had here, except this time it will be negative. Why is it negative? That's because point A is below point B. It's in the negative y direction. So that's going to be minus square root of 4b squared minus x squared over 2. Just make sure that everything is fine, and then 0. So let's see what we get. So we get the velocity of A is equal to this first thing, which I'm just going to write again, I don't really have a choice, minus omega bc, and then we have square root of 4b squared minus x squared over 2 multiplied by I plus omega bc and then x over 2j plus, right, and then let's try to deal with this determinant as well. So first of all, we have I multiplied by 0 minus that, so it's going to be omega AB times the square root. So 4b squared minus x squared over 2 times I, and then minus j times. So we cross out the j and we have 0 minus omega AB x over 2. So it's going to be omega AB x over 2. So that is it in terms of the velocity of A. And it doesn't really look like we got anywhere because we don't know anything about the angular velocity of BC to begin with. And the question is actually asking us to find this as well, omega AB. And this is where we have to use some constraints. Because if you think about it, if you look at the diagram, the velocity of A is purely in the x direction, right? Which means you can write that the velocity of A is going to be the velocity of A in the x direction, whatever that is, multiplied by I. But then point A is not moving vertically. It's constrained to move in a purely horizontal fashion, which means the velocity in the y direction is 0. Okay, which means that for two vectors to be equal, and we have two vectors here, so we have this vector on this side, and we have literally everything else on the other side. So for two vectors to be equal, the components must be equal. So the y component on the left is 0, the y component on the right is, let's see, so it's this, plus this. So we have omega bc x over 2 plus omega ab x over 2. So the x over 2's cancel out, so we have omega bc plus omega ab is equal to 0, which means that omega bc is minus omega ab, which is an interesting finding, right? So this tells you that the angular velocity of this member has the same magnitude as the angular velocity of AB, but they rotate in opposite directions, which makes sense. So in this case, if the acceleration here is to the right, BC will rotate clockwise and AB will rotate counterclockwise with the same value of angular velocity. So that's one unknown out of the way, but now we also have to figure out how do we actually find this. Okay, and to find this, we need to know something about the x component of the velocity of point A. And we do kind of know something about it, because the question tells us that at the beginning, or the initial value of x was 0. And from that point onwards, point A, which initially was here, was like very close to point C. So from then onwards, point A moved a distance x with an acceleration of A, with a constant acceleration of A. So what we can then say is that, well, we could use the Suvat equations basically. So we have v squared minus u squared over 2 s is equal to A. So that's essentially what we're going to use. So if we put the numbers in here, we have v a x, or not the numbers, but the values that we know, squared. The initial speed was 0. The acceleration is a, and the distance is x. So we have VAX squared is equal to 2xa, or you can say that the velocity of A in the x direction is the square root of 2ax. And that's it. So we can finally write down the velocity of A as the velocity of A in the x direction times I plus the velocity of A in the y direction times j. we know this is 0 from what we discussed earlier, which means the velocity of A is just square root of 2ax times I. And that's it. So we're going to use it to find omega. So let's write this again. So the velocity of A, we said, is the square root of 2ax times I. And that's equal to, well, that's equal to this thing right here. Okay, so we know that those two terms, basically the y terms, cancel out because there's no velocity in the y direction. And we also showed that omega bc is minus omega ab. So if you put them in here, you'll convince yourself that the j terms cancel out. So the only thing that we have left is that omega bc, I'm gonna convert that to omega ab, right? So this here, remember, that's equal to omega ab. So omega ab times the square root of 4b squared, 4b squared minus x squared over 2 times I, and then plus the only remaining term is omega ab again, so it's exactly the same term twice, 4b squared minus x squared over 2 times I. So for this equality to hold, we must have that the components should be equal to each other. So this has to be equal to this plus this. So we have square root of 2ax is omega ab times the square root of 4b squared minus x squared. So omega ab, or just omega as the question refers to it, is square root of 2ax over square root of 4b squared minus x squared, which is what we had to find from the beginning. So this is how you find the angular velocity, by using Euler's equation for velocity only, and then doing a few manipulations and using some constraints rooted in common sense to be able to find what the expression for angular velocity is. Now, the signs are also important. So because of the fact that we essentially got this with a plus, it means the angular velocity of this length should be positive, which means that according to convention, AB is rotating counterclockwise. So let's check that. So we know point A is moving to the right, which means bar BC, is literally dragging point A with it, which means that bar BC is rotating clockwise, which means that bar BC is rotating counterclockwise, which satisfies our sign convention, which is the fact that this is, let me just get rid of this, looks like a minus, which satisfies the fact that we have a plus in front of our omega. And that's the end of the question.